HDMI basic technology and terms. So we'll get forward. So here's the basic HDMI technology. This is how it works. We have a cable, and inside that cable we have a whole bunch of single conductors and shielded twisted pairs. I'll show you each one individually as we go through, but notice that cable has those twisted pairs, but also notice the shielding on it. That orangey brownish color is the copper braid, and the silver on top underneath that is aluminum mylar. The aluminum mylar is for very high frequency RF kinds of rejection, and the copper braid is frequencies lower than 1 meg. So that has the shielding. Not all cables have all that shielding. Some of them just have the aluminum mylar. Copper is expensive, so a lot of companies, in order to reduce costs, will eliminate that copper braid, say, well, the aluminum will do just as well. Well, not necessarily so, especially if it's anywhere near power cables. So the copper braid is a really important part of that shield device. Now the connector is 19 pins, 10 on the top, 9 on the bottom row, and it should be shielded along with the cable. In a lot of cases, it's not. And the jacket should be a UL listed jacket, so you can put it in the wall. Now, if it's got a covering on it, like a cloth covering, that's not a UL jacket. So what we do is we just do our cloth coverings up to 3 meters, figuring that everything longer than that's going to go on the wall, and usually a 3-meter cable won't go on the wall. If it needs to be removed, it can be removed as a UL jacket underneath that cloth. So here's what connectors look like when they're economically produced. These are cables that were purchased in distribution. So they're brand names that you would know right off the bat. And what we did is we bought a number of them. These are 4 different cables, 4 different brands. And we cut the molded connector off of it, which is all plastic basically, and looked to see what was inside. And you can see that it's exposed. All the solder connections are exposed. There's no shielding to prevent any EMI or RFI ingress into the cable at this point. And that's another cost savings issue. So what we do with tributaries, all our cables are made this way. We use a copper tape. It's a copper foil, actually. It's a copper foil, and it gets wrapped around the connector connections and soldered. Notice it's soldered on both the connector head and from the shield of the cable. So that means that that shield is continuous from tip to tip. So it's continuous shielding. So that means that it's going to be protected from EMI, RFI, cell phones, Wi-Fi, TV, all those kinds of things can have an impact. Also, it can have an impact on the radiation from the HDMI cable. This high frequency digital signals if allowed, will radiate like an antenna, broadcast that signal into the room, so it can disrupt Wi-Fi. And that's been an issue. If you go online and you look and Google and just type in HDMI and interference and Wi-Fi interference, you'll get a whole list of people complaining about having problems because their HDMI cable was interfering with their Wi-Fi, or could be with their TV signal, also could be with remote control, RF remote control signals. So shielding is really important, but it's expensive. It's not cheap. So our cables are a little more expensive, but there's a reason for it, and the reason is because we put a lot into this particular part of the design. So moving on. Multi-channel signal cable. Within this cable are various channels of signal, and they're all different, and some are going in 2 directions at the same time. So you have video and audio going through 3 separate channels. Then there's a clock channel, which regulates that video and audio signal. Then there's a communication channel. This is a 2-way communication on the digital display channel. And channel carries EDID and HDCP. Really important. This one makes it all work. And then there's a 5-volt power channel. There's also a cable, a conductor for the hot plug detect, CEC, which is a remote control figure from HDMI, and then the Ethernet. So inside, this is what it looks like inside the cable. So here you have what we call D0, D1, and D2. And they're shielded, twisted pairs. So you've got this aluminum mylar shield around a twisted pair. These three carry the video signal and the audio. Now the audio is a very small portion of the overall digital signal, but all three of them carry that video signal. Then there's another one that's a clock signal. Okay, where do my signals go? Let's see. Okay, hold on a second. It looks like we have a little, my PowerPoint is right now in thinking mode. Okay, here we go. So there's the clock channel. So the fourth one is the clock channel, and that regulates the video and the audio. So altogether, these guys are responsible for the video and the audio signals. Then we have another shielded twisted pair, and this is that DDC line. The DDC line is the one that carries the EDID and HDCP. This is two-way communication here. So the signal is going back from the source to the display on a continuous basis. Ethernet. Now this is not used very much now. It will be in 2.1. It will be the conductors for EARC. The new audio return channel is going to be on the Ethernet channel. And what that means is you'll have much more robust than the ARC we have now. 5-volt power is on a single line, and then the hot plug detect and consumer electronics controls have their own. So these are all the different conductors and what they're doing internally inside this cable. So here's how it works. This is the physical transmission that occurs. So we have to say we have a source on the left side and a display on the right. So the source could be a cable box. It could be an UHD Blu-ray player, whatever. The display, of course, is a TV or projector. So now what we're going to do is we're going to connect an HDMI cable between the two. As soon as we do that, a hot plug detect signal is sent to the source, alerting the source that there's been a connection. As soon as that occurs, the source turns on the 5-volt supply to the display HDMI electronics. In other words, the HDMI electronics in the TV is now awoken. And when that wakes up, it now sends back to the source the EDID information, because the source has to know, what am I connected to? What are your video capabilities? What are your audio capabilities? So that it can set up the output for the best picture on that TV. So all this is embedded in the EDID information as it goes back to the source. Also is the HDCP content. Now the HDCP are really, they're keys. They're encrypted keys that go from the display to the source. The source has to know that it's connected to a TV and not to a recording device. And it does that through encrypted keys. Once the source authenticates the key as being from a display device, then it turns on the video. And when the video is turned on, then you have the picture. Now, the other thing that's really interesting is that HDCP encryption keys occur every 2 seconds. As long as they're connected, every 2 seconds, HDCP is sending the encrypted keys. And then the source authenticates and continues the video stream. If it doesn't get that key, it shuts off the video. So that the ability for the cable to continue to conduct that signal and transport that signal is extremely important because of HDCP. So that's how it works. So let's talk some terms, some basic terms. First one is resolution. On a flat panel screen, resolution is made up of columns, derived from columns of rows and pixels. Each pixel has 3 parts, red, green, and blue. The number of pixels on that screen determine what the resolution is. So, a resolution for a 1080p panel, 1920 by 1080, total pixels, 2 million. 4K panel, 30, 40, 20, 60, 8 million. Now we jump from 2 million to 8 million. And then when we get to 8K, we go up to 33 million pixels. So looking at these three, 2K, 4K, and 8K, 2 million, 8 million, 33. It's a factor of 4 each time, multiplied by 4 to go from one to the other. And remember this, somebody says, well, I've got a 4K set. The only thing you know when somebody says I've got a 4K TV is that it has 8 million pixels. That's it. You know anything about color depth, you know anything about color, about the rest of the color possibilities, and also you know anything about frame rate, you know anything about HDR, SDR, just 4K. And remember, in the beginning, those 4K sets in the beginning did not have HDR capability. They did not have deep color capability. All they had was 8 million pixels. And then people were very disturbed to find out that they couldn't run their HDR through their TV and they had to get a new one. So, but that's the important part of resolution. Those are just the numbers of pixels. Each pixel has 3 parts, red, green, and blue. And the important part about that is, in order for that pixel to emit the correct color, it has to have a palette of shades to draw from. So it has to draw shades of red, of green, and blue in order to emit the correct mixture of those for the color that it's supposed to emit. So each pixel has to be instructed. Each part of each pixel has to be instructed as to which shade of red, green, or blue to emit. That's what we call color depth. It's all about the shades. All about color depth is all about the shades. So let's look at 8-bit color. 8-bit color allows 256 shades, or 16.8 million colors. That's 256 red, 256 green, 256 blue, for a total of 16.8. Now my TV at home is a plasma, and it's an 8-bit color. And unless you have one of the new TVs, the LEDs, the QLEDs, and so forth, you probably have an 8-bit set. And 16 million colors is a lot of colors. That's what I thought. Sure, till I started doing the research and looking at what this is, and I was pretty well dumbfounded when I found out that 10-bit color, which is the next one up, is 1.1 billion colors. So it jumps from 16.8 to 1.1 billion. Huge jump in color capability, just going from 8-bit to 10-bit color. And of course, the human eye sees that color change as a very positive thing, where the resolution, it may not see the difference between 4K and 8K, especially if they're more than 10 feet from the screen. If they're standing 2 feet from the screen, yes. Just seeing 10, 12 feet back from the screen, they probably can't tell the difference, but you can tell the difference with the color. And the other one is contrast. That's the other major difference between these sets. 12-bit deep color, 4,096, 68 billion colors, 16-bit colors, 281 trillion colors. All of this is resolvable by the human eye. The human eye can see all these colors. That's all within the spectrum of human sight. So you can see we've got a long way to go on color, but that's what's going to make these sets even better looking. So let's tie in color depth and color space. The chart on the right was determined, created in 1931 by the ICU, and that is all the colors that the human eye can see, called the available color gamut. It's really kind of interesting because if you notice that most of the colors in there are green. The preponderance of color is green, because that's what the human eye is most sensitive to, is the shades of green. Notice blue is very small and red is kind of in the middle. So we see green more than we see any of the other colors. The D65 is white. That's the accepted component for white. That's how much is a specific amount of red, specific amount of green and blue that comprise D65. But that's what the industry has accepted as white. So everything comes from that point. So looking at color depth now in this color space, 8-bit is the smaller triangle, the dashed lines, 30% of all colors. So of all the colors the human eye can see, only 30% comes out in 8-bit color. So that means my TV is missing 70% of the colors. I didn't know that. I thought my TV was just doing fine. Little did I know. So now I really want a 10-bit screen or a 12-bit screen because I want more color. 10-bit is 50% of all colors is 10-bit, and 12-bit, which is Dolby Vision, by the way, is 75% of all colors. It'll be a while before we get to that 16-bit number. I think numbers of years away. But 12-bit would be, that's the, the magic number, 75% of all colors. And that is achievable with Dolby Vision. But not saying that just because it's Dolby Vision, it can do all 75%. That has to be in the spec, but it has the capability of that. So that's color depth and color space. Now, looking at color depth, what is the real world meaning of that? Well, look at the top bar. That's 8-bit. The top horizontal bar is 8-bit, bottom is 16-bit. Notice in the top bar, it has all that banding. Well, the banding is because the colors as it moves across that chart doesn't know all the shades. It doesn't have it in its palette. So it keeps reproducing the same shade that it knows until it comes to one it doesn't know. Then it can't reproduce it until it comes to one it does know. Then it reproduces that one. So you get this banding effect. Here's what it looks like in a real picture. On the left is standard color, 8-bit color, and the right is deep color. Notice the sky. Notice the banding in the sky. That's what happens. 8-bit color. Where deep color, it's nice and smooth, very smooth transition in the shades of blue. So that's the difference between them. Color sampling. This one takes a little bit of time and can be a bit tricky, but here's the deal with color sampling. Chroma sampling or color subsampling is a method of encoding images by requiring less resolution for the color information than for the brightness information. So we see color and we see brightness. Those are the two parts of what we see in an image, brightness and color. We see brightness much more clearly than we do color. So what happens is color subsampling lowers the resolution of the color part of the image, but keeps full brightness. This method takes advantage of the human eye's lower acuity for color differences rather than luminance. And Wikipedia, by the way, has a number of really good pages on this. So 444 captures all colors. It's not subsampling. 444 is sampling, and that's all frequencies. All colors. Subsample starts at 422, and they do that by compressing the color data, and that's done by lowering the resolution of the color data. 420 further increases the compression. Now, this is all derived from component video, YUV. Y the Y component, remember the component video, the 3 cables, green, red, and blue cable. Y was the luminance, the black and white information was on the green connector, on the green cable. U was, we call the red difference signal. That was the one part of the color component, and blue difference. Now, why did they do this? Why didn't they just have a color connection? Why do you have to go through all this jazz? Well, it happened basically because of black and white TV and color TV in the 60s. When that was introduced, there were 99% of the TVs out in the world were black and white TVs. RCA had developed color, and you remember Walt Disney's Wide World of Color. They wanted to broadcast that in color. Well, if they broadcast an RGB signal that is all color, number one, it wouldn't fit within the FCC boundaries for the channel selections. Remember channel 2, 3, 4, up to 13? Well, that had a bandwidth, and the signal had to fit within the bandwidth that was allotted for each channel, or else you'd be over in the next guy's channel. Well, RGB was just too big. It couldn't fit into that. So they had to come up with a method of reducing the bandwidth requirement or reducing the data so that it could fit. And they came up with the YUV. They separated the black and white information from the color information. Then they sent out both those signals. They were able to get them within that, in that context. If you had a black and white TV, it would accept the black and white, the Y information, and you'd have a picture, and it would just disregard the U and V. It didn't know what it was. If you had a color TV set, it would know what they are, put them together, and you'd have a full color image. So that's how this all came about. And then we use it for component video. And Now we're using it for color sampling. Notice in those numbers 444, 422, and 420, the first number is always 4. That is the Y information, the luminance. So there's always the full amount of luminance for every pixel. So every pixel has the correct amount of brightness. The color, which are the next two, the U and the V, that is subsample. So they're not giving us all the color information. What they're doing is they're asking the pixels to share color. And they're sharing it 2 times for the red and the blue and the 422, and then only 1 time on the red side. So what happens is we have this effect. The top row is the actual picture with the color. And you could see starting at, well, 411 we don't use, but 420, 422, there's hardly any difference in that picture. Now, we're looking at it on a small screen. If you had this on a big screen and you walked up to it, you'd look at it, you could see the difference in the resolution. It's the resolution that's being compressed, by the way. So the bottom picture, that's the same picture with the color removed. So it's kind of like the skin has been removed, and those are the bones. And you can see what happens, how the resolution increases going from 420 to 444. But as soon as you throw the color on it, it's hardly noticeable, unless, again, you get up close. So that's what happens. So this is the way that they reduce the file size and the transmission size in order to fit all the data in whatever the transmission carrier that they're trying to use. And by the way, this is also used for JPEGs. So if you take a full RGB picture and you put it into a JPEG format, it's going to reduce the file size dramatically, and it's doing the same thing. It's reducing the color components, but keeping the black and white or the luminance information consistent. So there's your color sampling. So 444 is all colors, 422 is reduced. So 444 captures all colors, 422 reduces the color data by 50%. Huge dramatic savings to do it that way. And then 420 reduces the color by 67%. And there's very little reduction in picture quality with this. So that's color sampling. So let's look at now resolution, color, and data rate. Let's tie those together, how these work. Well, it's all mathematical. The bits required to produce one still picture, a 4K picture using 8-bit color and 444 color sampling. That comes out to 291.9 million bits of information. Again, this is all mathematical. Now, if you take that and you say, okay, I want 60 frames. That was 1 frame. How about 60 frames? 1 second of video. Okay, you just multiply that 291.9 million times 60, and it comes up with 17 billion bits is required in order to produce 1 second of video at 4K resolution, 8-bit color, 444 color sampling. 18 gigabits. That's where the 18 gigabits comes up for the upper limit of HDMI 2.0, 18 gig. So let's go back and take a look at at HDMI, starting with the 4K introduction. HDMI 1.4 introduced 4K capability in 2013, and it was 4K at 24 frames. 10.2 gig, that's three channels. Remember the D0, D1, D2? Each one of those had to be capable of transporting 3.4 gigabits per second and 8-bit color. Then the following year, in 2014, they introduced 2.0. And now they bumped the frame rate from 24 to 60. So we literally doubled the data rate, going from 24 to 60. We increased the actual data rate capability for the cable and for all the systems up to 3 channels of 6. So we went from 3 channels of 3.4 to 3 panels of 6. So now we're doubling the data rate. And we've added 10-bit and 12-bit color. Of course, this was the big change. 12-bit, 10-bit, and 12-bit color now are available. And 420 color subsampling was added. This wasn't used before because it wasn't necessary. We had enough bandwidth in the systems previously. But now with 2.0, we needed to reduce the data because we've increased the resolution and the colors, the color depth. So now we can reduce the color sampling so we can fit all this stuff on a disc. That was basically what they did. 2.0 was static high dynamic range, and that's high dynamic range is averaged over the entire movie. So the dynamic range of the movie is one figure basically over the entire movie. Dynamic range, the difference between the highest or the brightest and the darkest part of the image. And it's a brightness of the individual pixel, not the entire screen, just the individual. How bright can we make that pixel? Brightness is measured in nits or candelas per square meter, which is the technical term for the brightness level. But they've shortened it and said, okay, we're just going to call it a nit. So how many nits? TVs, my 8-bit color screen at home is 100 nits. And if you have a 8-bit screen at home, plasma, whatever, it's going to be 100 nits also. Go to movie theater, it's 100 nits. 100 nits is about the maximum for years and years and years. Now that's starting to change with the new TVs. HDR requires 10-bit or 12-bit color. This is really important because if it's an 8-bit screen like mine, I could never watch HDR, could never have an HDR picture. It requires 10-bit or 12-bit color. So that's a very important characteristic to know. HDR requires 10 or 12-bit color. So here's a standard dynamic range photo. And I'm not sure what the resolution is. It really doesn't matter. But the color and the brightness levels are there. And it overall looks like a pretty nice picture. I mean, you can see the State House there, St. Louis, and you can see the arch in the background, the Hyatt sign up on top of the building, the trees. I mean, everything's there. The resolution is good until you see what it looks like in high dynamic range. And you say, oh my goodness. Well, what changed? Did the resolution change? Not really, but what changed was the colors. Now we have colors that we didn't have before, shades of color that were not available on that standard dynamic range. And because we can see things in that arch, the reflections in that arch that we couldn't see clearly in the first picture, it looks like the resolution's increased. The amount of colors, you look at the dome, that green, that shade of green just wasn't available on the 8-bit screen, but on the 10-bit color, it's there. And of course you can see the brightness, and that's from HDR. So now we have pixels that can get brighter than the standard one. So there's a lot of improvements that come along with high dynamic range, and it's the essence of why anybody would want a new TV. They may not know it, but that's why they want it, is because of this one function, HDR. And that requires deep color, and it requires the ability it requires an 18 gig signal and an 18 gig cable. That's the real function. Here's a chart that shows the data rate capabilities that for different resolutions and frame rates, bits, color depth, color sampling, and data rates. So you can see where the Blu-ray disc starts at 1080p 24. UHD Blu-ray disc is at 2160 24, and then the maximum for the Blu-ray disc, and then 8K starts there. And then you got that one, that dark blue in the middle between the two there at the bottom, or at the bottom of the pink screen, or whatever color that's. I guess that's called salmon. I don't know. Liz, that's salmon? Ladies know that. I'm not sure. But it's below that thing, that darker blue, that's kind of in the middle. 2160/60 10-bit 444. That's 4K, by the way. 4K 10-bit color 444 screen, but it's 20 gig. So an 18 gig system could never show that. You'd have to have a 2.1 system to be able to show that 2160/10 444 at that require 20, but it would only be 4K. If you want to go to 8K and you wanted to do that, and you wanted to be able to do it with HDR, you'd have to go to 32 gig. So, and the 48 gig uncompressed 2.1 limit is at 48. So that's uncompressed. Compressed, we can go through about 130 gig compressed. So here's some UHD Blu-ray issues, UHD native spec, what's on the UHD Blu-ray. By the way, there's only two ways right now, two ways to have uncompressed full 18 gig performance content. That's full 18 gig uncompressed. Only two ways. One is UHD Blu-rays. Two is Kaleidoscape. Download the movie overnight or how many hours it takes onto your Kaleidoscape processor and then play it from there. That's the only way to do it. Everything else is compressed, whether it be Netflix or Amazon Prime or any of those. That's all compressed video. They have to put it on the internet, so they have to compress it. So on the Blu-ray, you can do 24 hertz or 60 hertz movies that are shot in either 24 or 60. Now, most movies are 24, very few are shot in 60. 10-bit color or 12-bit color is available on the disc as native. 420 is the maximum color subsampling that's available on disc. But the player can upconvert that to 422 and 444. That can be done. We generally say don't do the 444 because it can cause issues with the rest of the equipment in this, especially if there's a receiver or switching system involved in it. It's always best to keep it at 420 or 422. So when you're setting up the Blu-ray player, 4K 60, 444, 8-bit, you can do that, but it won't allow HDR. Remember, this is 18 gig now, so you can't go more than that. So if you try to go to 10-bit color, that would be 20 gig, so it won't work. So what you can do then is drop the color sampling down, subsampling down to 422. Then you could do 10 or 12-bit and have HDR again, which gets a much better picture, or drop the frame rate to 24. Since most movies are done in 24, you're not going to lose anything by going to 24 frames. It's the native rate. Okay, HDMI extenders. Let's take a look at this. HDMI extenders based on HDBaseT technology, owned and licensed by a company called Valens in Israel. They're the developer of the technology, and they own it and they license it. Maximum uncompressed signal, 4K, 30 frames, 444, 8-bit. That's 10.2 gig. That's the max. That's all HDBaseT can do. So what they've done, because they haven't been able to come up with an 18 gig, true 18 gig solution, they came up with data compression. So now what they're doing is they're compressing the signal at the sending end, at the transmitter, and they send it down the Cat5, Cat6, and then it gets decompressed on the other side to come up with the 18-bit. Now it's perfect for all the peripheral TVs. I mean, kids' room, the bathroom, the workout room, it's going to work fine. People will love it, no question. But main viewing area requires uncompressed data. And the only way you can do that is with a cable that is certified to perform at 18 gig. So that's the important part of HDMI extenders. They're also the cables are generally a lot less expensive than the extenders and a lot less to install and a lot less to go wrong. So we now have cables that are certified 18 gig out to 164 feet. Something to think about when you're doing installations. Another thing is HDMI extenders are only good to 10-bit color. They don't do 12-bit color, not in the tech, not in the spec. How do we test for HDMI? Cable performance tests. Well, there are basically three methods, three things we do for testing. Eye patterns, insertion loss or attenuation graphs, same thing, and rise time. And I'll give you examples of all three of these. Here's the eye pattern. So the eye pattern looks like an eye. That's why it's called an eye pattern. What it actually is a million or more square waves that are averaged over one frame. So this is done on what's called a time domain analyzer, which is a really fancy and expensive oscilloscope. So it looks at a data stream, like this video data stream on one channel, one video channel, the D0, and it's going to average all that data stream onto one frame. So, and it inserts that blue mask in the middle, and the blue mask is going to help us determine if the waveform is actually performing properly. And the way it's done is if that orangey yellow line starts to get too close to mask, that means it's collapsing. And if it's collapsing, that means that the whole waveform is going away, which means it's failing. It's not able to move that signal and transport the signal. So this is how we determine the video capability of the cable. We look at the I pattern for each of D0, D1, D2, and clock. And we make sure that the I patterns are consistent for all 4 channels and that there's a pass-fail configuration. This is amplitude, and frequency is the left to right. Also, another thing we look at is, you see where they cross on both sides, the X's? Well, if that X is too wide or dispersed, it indicates that there's a lot of jitter. And that's a manufacturing issue. Cable wasn't made properly, twists per inch are wrong, and the pitch is wrong. Something's wrong with the manufacturing that causes it to have timing issues. The second one is the attenuation or insertion loss. Now this is this graph. The horizontal axis is data rate, 0 on the left, 6 gig on the right, and attenuation or volume level, if you'd like, on the vertical screen starting at 0. The black line is the line from HDMI that says this is minimum performance. The cable performance has to be above this line. The red line is the cable under test. Now we divide it from Rev 1.4 to 2.0, which is basically 1080p on the left and 4K and above on the right. So the cable being tested now is a 3-foot high-speed cable. High speed is a very important term because it means that HDMI has certified this cable in their testing centers, authorized testing center, as a cable that will perform up to 10.2 gigabits per second. All manufacturers have to have their cables certified at least this performance. When they do that, then they can use the HDMI logo. So if it has an HDMI logo on it, that means at least it is a high-speed cable, 10.2. When you look at that red line, though, it stays well above the black line. So you think, wow, that looks pretty good. However, there's a lot of nonlinearity in that. It's bouncing around a lot. It's ringing, actually. There's a lot of high-frequency ringing. So there's a lot of lost energy. So when you take a look at this, you say, well, what does the I pattern look like? Because these two work hand in hand. So the I pattern at 10.2 or 3.4 gig times 3 would be 10.2. Since we're only looking at one channel, 3.4. It passed. It's very nice. Good open eye, really far distance from the lines. But when we look at it at 6 gig, it fails. So this cable would work great for 10.2, 1080p, or basic 4K. But as soon as you try to turn on HDR or use an HDR disc or an HDR content, you would get a black screen that would say it's that it's non-performing or it doesn't, not working, black screen. So that's the interesting part about these cables can work in one situation. Here's another issue. It's a 1.5 meter high-speed cable. This one, look at that curve, it's gorgeous. It's 8 decibels of loss all over 6 gig. That's a pretty amazing. And look at the I pattern for 10.2, or excuse me, for 1080p is big open eye, so it's really working well, fast. But try to run that at 18 gig, it doesn't work. And the reason is jitter. The timing, there's timing issues with this cable. So when it was made at the factory, something was wrong with the manufacturing process. And here's where it shows up, is in jitter, timing issue. Could be that one half of a twisted pair was longer than the other by a few thousandths of an inch, and one part of the signal arrives before the other, and the whole thing shuts down, so it wouldn't work. This cable has obviously got a problem. It's all over the place. Fails at 3.4, and it's completely obliterated at 18. So this won't work at all. This would be a DOA. This is our UHD-S cable, our skinny cable, 1 meter. And there's the performance at 1080p and 18. Really beautiful, 2 gorgeous eyes. Rise time. Now this is the third test. Now the rise time is what we test for square wave, and this has to do with the DDC channel. Remember the DDC channel that carries the HDCP and EDID information. This cable this channel runs on a totally different protocol than the video. It's running on what's called I²C, which is a whole different way of moving these square waves. So this one has to be looked at completely differently. You don't do eye patterns at this one. This one is rise time. So now we want to see is how much time does it take that square wave to go from the 0 up to its 1, its max. Slow rise time is the reason that most long HDMI cables fail. And it's measured on this DDC line. And if the DPL requires a rise time of less than 1.5 microseconds, 1.5 millionths of a second. So here's what it looks like. There's the generator output. So the generator output 0 to 1 in 0 time because it's straight up. It's a generator. But as soon as we connect a cable to that generator before it goes to a TV or to wherever it's going to, the cable's capacitance is going to roll off that leading edge, and it's going to look like that. Now the time to go from 0 to 1 is extended. So instead of 0, it's going to be something greater than that. If it's more than 1.5 microseconds, the cable fails and you get no picture. And this was this was happening with all the long cables. So many of the long cables early on that nobody understood the capacitance of the cable was causing these difficulties. That's pretty well not the case. At least I know for our cables, it's not the case anymore. So performance verification, how do we do this? Okay, so we have a company in Taiwan that we work with on our HDMI cables. They manufacture them in China and in Taiwan too. And we go to this company, say, okay, we want some new cables and they have to be 18 gig performance. So we tell them what kind of size we want, what gauge, the insulation, all these kinds of things. And they produce samples. When we get those samples in, the first thing that we do is we send them to DPL for certification, because our Chinese brothers tell us that it's 18 gig, but like Ronald Reagan, we trust but verify. We know these are good guys, but stuff happens, right? So we send it up to DPL. They do a complete evaluation of it. If they come back and they say, yep, they're 18, they meet all the specifications, then we go to our manufacturer and say, here's our purchase order for how many thousands of cables make these for us. Then when we get them in, we send samples back up to DPL because we want to make sure now with the production models are also verified. So DPL then takes 5 samples from every length and does complete verification. If they all pass, then we sell them. Then we start to actually market and ship them. But it goes through that whole sequence before we as a company, tributaries. Now, I don't know about other companies. I don't think they go through what we go through. But I want to make sure that those cables go out and they work. I don't like to have phone calls from dealers that are having problems because the cable failed for some reason. So DPL Labs is the only lab in North America that has that capability of doing this kind of performance analysis of an HDMI cable. They use the most sophisticated HDMI test equipment available, and they can test every channel in that HDMI cable to make sure it's performing properly. They provide us with the iPad insertion loss rise times for each cable. So there's the mark. When it has that seal on it, and we put that on all our products, whether it's on the displays or the bags or whatever, they're always marked as DPL certified and certifies all the different parts of the cable. And we have all this documentation available. So if someone says to me, hey, I want to see the eye pattern for that UHDP 5 meter, we say, no problem. And we'll send it to them so they could see it. And we have all this information for all our cables. We're the only company that I know of in the industry that has this information and is ready to send it and share it with whoever needs to see it. No other company, they make all these claims, but they don't share their test equipment, maybe because they don't have it. We find that some companies actually in China are testing their cables with a Sony PlayStation. That's how they're checking them to make sure that they do what they're supposed to do.
Interesting.
So ATC, which is the Authorized Testing Center of HDMI, has this program called Premium HDMI Cable with that sticker. And that sticker is available for companies who buy this program, and they can put it on their product. And what we found is that they only testing passive cables and only testing the video performance. They're not testing the DDC channel. So they're not testing that to make sure that it has full integrity, or they're testing the other parts of it either. So it's a limited test as compared to our 4K that we do at DPL, where they're testing everything in the cable. So if a cable company says that they have cables that are 18 gig or worse, they say 2.1, say, great, where's the documentation? Where's the I patterns, graphs, and rise time specifications? If you make a claim, you got to back that claim up to make the claim. And I'll tell you, most of the time you'll get crickets in the background. Here's our digital over fiber. This is, of course, this is the new evolving part of the HDMI cable business is optical cable. So we got multi-mode optical fiber, optical multi-mode numbers, and VCSELs, vertical cavity surface emitting lasers. Lasers are what are required for fiber optic HDMI data transmission. So you have optical cable, you have an optical mode number for the cable, the cladding surrounds the glass core, it's opaque on the outside, mirror on the inside, highly reflective, and then there's a core, the glass core. You can use an LED or you can send the signal with a laser, either one. OM1 cable is 1 gig, as is OM2, OM3, and OM4 are 10 gig cable. And LEDs for OM1 and OM2, OM3, and OM4 are laser VCSELs. All our tributaries, laser cables, fiber optic cables are all OM3. So we can do 10 gig. And if the chipsets are capable, that's times 4. So that could be 40 gig, or it could be 2.1 cable. And we believe that the Aurora cable, the original cables that we were selling optical, are 2.1 cables, but we won't know that until we have full testing capability. Testing specs are released.
You leave your sunglasses, everything on their speakers.
So what's under the hood in the fiber optic HDMI cable? So there's the cable, it's a connector. So there's the glass, there's the fiber core. Inside that's a mirror. So then we have the HDMI in. The HDMI signal comes in, goes out into the VCSEL. The VCSEL transfers it from electrical signal to light. The light then gets emitted from the VCSEL into each of the different cores. So you have the 4 signals, the D0, D1, D2. Each one gets emitted and reflected into the individual core, and then it goes down through the cable. Comes out the other end, gets detected, turned back into electricity, and that's how the fiber optic cable works. So when we transitioning from HDMI copper cable, basically the fiber, as we go up in HDMI data rate, as we increase the data rate, the loss or the attenuation in the cable increases. So what we found is that for 10 meters, we can go pure copper, passive, no electronics. We can now do 18 gig. That's our Titan 10-meter copper. So we can do that passively. Active copper, we can go past 18 gig, but yet we don't know how far because the testing specification isn't available beyond 18. So we don't know what that's going to be. Fiber cable, we can go from 10 meter out to at least 50 and probably, I don't know, a quarter mile. I don't know what that's going to be able to give us. That's all being worked on now. So we'll see. That's definitely in process. But fiber is definitely the way of the future for these types of cables. And a lot of this is dependent on the silicon, on the chipsets. We know the fiber can do it. It's the electronics that supply it and decode it on both sides that are the determining facts. Choke point is right there. Where is it? Is the silicon available to do this? So the active optical cable, it's called AOC cable, and that's fiber optic and copper, both hybrid. The fiber carries the video and the audio signals. Remember D0, D1, D2, and the clock. And the copper carries everything else. So we have copper conductors for everything but the video and audio signal and clock. Now, some of the cables, like ours has a smaller connector for the display end. That's a two-piece. So you take the head off, and it's very small then, and you can pull it through a conduit easily. And we include the pull device to protect that head of that connector as it's being pulled. And then when it's through, you can then just put the connector back on, tighten it up, and it's done. And the power supply is at that display end. And that USB power supply is important because it makes sure that the chipsets have a consistent 5-volt supply. It's not dependent upon the source for this voltage. In other words, the Blu-ray player or the cable box. So let's look at HDMI 2.1. This is the new development that was introduced in 2017. You know, it's over 3 years ago. 3.5 years ago it was introduced. We're still struggling with getting to the specifications for testing for the cables. We still don't have it. All the feature sets of 2.1 are not supported by all manufacturers. We don't know how this is going to work. What is going to be constituted as a 2.1 cable? Does it have to be able to conduct and to actually work with all the features, or just some of them? We don't know yet. The maximum uncompressed data rate for version 2.1 is 48 gig. So at 4K, that would be 120 frames, 12-bit color at 444, or at 8K, 60 frames, 12-bit at 420. That's 48 gig. Compressed at a 3-to-1 ratio, we can go at 8K to 120 frames, 12-bit color, 422. That's 128 gig. So there is a compression capability with HDMI for this to happen. 48 gigs, 4 channels times 12. Remember in 2.0, it was 3 channels of 6. Well, now they've gone to 4 channels of 12. I'll show you how that happened. Dynamic HDR means that the high dynamic range is available frame to frame. So it's the exact dynamic range, the way the director wanted it in the movie to start with. So it's the original. Variable refresh rate for the game, EARC, much more robust object-based audio for Dolby Atmos and DTS:X, fixed rate link training. This has the ability to down convert the output of the source in order to match whatever the cable's capability is. So if you have a cable and you put it on and you think it's 48 gig and let's say it's only 18, well, the system will be able to determine that and reset itself for 18 gig. Now, that, I don't know, to me, that's a double-edged sword. It works, but then you're not getting what you think you're getting. So we don't know how this is going to hang out, whether they'll be on-screen display so you'll be able to determine what you're looking at, what color depth, what color sampling, what is the refresh rate, what is this? We won't know yet. I don't know what the manufacturers are going to do, but fixed rate link training is part of the spec. So the technical specs were released for 2.1 in November of 2017. Compliance testing for the sync and the source were available in 2018, but we are still in 2020 and we don't have the testing for the cables. So we're waiting for that. How did they get 3 channels? How did they go from 3 channels of 6 to 4 channels of 12? Well, what they did is they took the clock channel and turned it into another data channel. So now we have 4 data channels, and they have embedded the clock within the data channel. So we have D0, 1, 2, and 3. So this is right from HDMI. This is courtesy of HDMI.org's website. Testing and certification. What is the testing policy for HDMI 2.1 products? This is right from HDMI. All products must comply with version 2.1 of the HDMI specification and the compliance test. And until the CTS is available, whenever, and a product has passed compliance testing, a product cannot claim to be 2.1 compliant or market it that it supports 2.1 features. So if you go on the internet now and you go to Google and you say HDMI 2.1 cable, you'll get a ton of different cables that are all advertising 2.1. How is this possible? Well, HDMI allows it. I mean, HDMI can go on. They can go on to the internet and see all this, and they could send those guys. I mean, when we first started selling HDMI, I got a letter from HDMI, a cease and desist letter, because I was not an HDMI adopter. They said, we don't know who you are, and you're using our trademark, HDMI, cease and desist, or else we're gonna sue you or whatever. Well, I let them know that we buy our cables from an HDMI adopter, so that's legal, and they left me alone. Then they sent me another one because I wasn't using TM when I had the HDMI logo. They were going to come after me for that, would you believe? But they let these guys market this stuff all over the internet, and they don't say anything. So there's no policing of this. So you just have to know that this is the situation. So then the question is, when will the certified testing specifications be available? Well, they additional features will be added in the coming months. So basically they're saying, we don't know. And we believe the holdup has to do with the eye patterns, and they're determining how they're going to set up that mask in the eye pattern. Is it going to be a real small mask or a big mask, which will determine pass or fail. So I think that's the issue. And we're still waiting to see how this is going to work out. So here's how we're going to have our certifications. We're going to have DPL certify our cables. As long as they're certified. Remember, it didn't say they have to certify them, because for them to certify them is a really big deal and a very expensive deal. So DPL is going to do our certification. One of the new things that's been added to it, or say emphasized more now, is the testing for EMI. That means that the shielding on these cables has to be sufficient to keep that signal in the cable. Otherwise, it will go out and it will interfere with Wi-Fi, with TV signals, remote controls, all these kinds of things. So the HDMI EMI testing is a major test that's being added to all these certifications, and also a very expensive certification test it is. So we'll probably do some of each, but DPL Labs will be the major certification for us. We will do some ultra high speed also. Now, in addition to all that other testing, it's really nice because we know that the cables have been certified, DPL certifies, but what about every shipment that we get in? I mean, we're getting thousands of cables every month. What happens to those? Nobody's testing. There's no certification for those. We're just, again, trusting that these are made the same way. So what we do internally is we test every cable. We use a Meridio generator that generates an 18 gig HDMI signal. And we hand connect that generator to a screen using 18 gig, 2160, 60 frames, 8-bit color, 444. And we generate a picture. And if that picture is, has the resolution, no sparkles, audio, color, everything is correct, then we shake it to make sure there's no intermittence in the cable, and then we pass it. And we do that for every cable, 100%, long, short, whatever. We have 100% testing. So every cable that we ship works. We don't ship bad cables. We don't let our dealers do quality control in their customers' homes. We do it here for you. All our HDMI cables, except for the Vega, the optic fiber cables, are lifetime guarantees. Lifetime warranties. There's a difference. There's a difference between a guarantee and a warranty. Look it up. So here are the two important characteristics of our cables. One we talked about, which is the shielding, and the other one are the power grips, top retention and side retention. And one of the reasons, this holds it in place, but there's one other part to it that's important. That is one of the pins, one of the receptacle pins on HDMI cable. It's pin 18. From the flat side, if looking at the cable from this direction, it's the one all the way to the far left. I'm pretty sure it's 18, pin 18. It's recessed. It's the only recessed pin in the connector. So when you're plugging it in, data connects first and then power, which is the correct way to do it. However, when it's plugged into a component, if someone moves the component and the connector isn't in tight, horizontally, it will move. And 18, pin 18, since it's far left, it will be the first one to disconnect because it will shift in position. It won't stay in. So it'll shift and disconnects and power goes out, and so the picture goes down. You have to reach behind, unplug it, and plug it again. Because of this retention, the side retention especially, it protects the connector from moving sideways. So any horizontal movement of the component, the cable will move with it. It won't allow the cable to detach and disconnect. Very important consideration. And we use that on all our cables except the basic UHD model. Basic UHD model does have some retention, but not as much as this. So here's the short length cables. UHD, HDMI, that's our basic go-to cable. Tight fitting, it has the medium fitting little, they're raised elements on there. So it is tight fitting and it is certified 18 gig, but we did ISF certification for inexpensive cables. That was basically a cost issue. And this cable is available from a 1/2 meter to 4 meter. Then we have the super slim cables that have the power grip connector and they're passive for a 1/2 meter to 2 meter. People say, well, how come only 2 meters? Because at that gauge of cable, 2 meters is as far as you can go and still claim 18 gig performance. So if you see cables that are real thin that are longer than 2 meters, they're not going to make 18 gig. Our Pro model, power grip, and it has more heavier gauge, more copper in there, and it's passive from a 1/2. We can now go to 5 meters with this one and still have full 18 gig performance. Now, some people say, well, you got a 1 meter cable, the UHD, that's certified for 18 gig, and then you've got the Pro model, that's a 1 meter that's certified to 18 gig, and I know the Pro models cost more than the UHD. Why should I spend the money for the Pro? Well, number one is the connector, the heavy duty power grip, but the other thing is that extra gauge is insurance for performance. You know, being with my Macintosh background, amplifiers, I'm a big proponent of headroom. I like to have extra performance over and above what I need, just because I know this equipment, there are times when it is required, and it's for best performance, that headroom really makes a difference. So having that extra gauge of copper can make up for deficiencies that elsewhere can occur in the system as far as low voltages or fluctuating voltages. So that UHD Pro is our top model. And I can tell you, on a quantity basis, on a per piece basis, we sell more of the Pro models than we do the UHD models. So most of our dealers are much more interested not only in performance, but also in dependability, making sure that they're going to work and they're going to continue to work. Now, if price is an issue, then use the UHD. I mean, that works fine, and it should give you great performance over time. But the UHD Pro seems to be the model that most people like. Long cables, UHD passive 18 gig. That blue cable is our Titan. That's a special copper that we use that has been treated properly, so it's more conductive than our standard copper. And because of that, we're able to get passive HDMI out to 10 meters. And that's been very unusual. There's not too many companies that can claim 18 gig performance certified out to 10 meter passive. 6, 8, and 10 for the passive Titan cable. Then we have an active cable that we call the X model, the extended active cable. And that has a built-in chip, no external power supply, so it's depending upon the internal supply that's coming from the source. And that's available at 6, 8, 10, and 12. 12 meters was as far as it would go and still perform at 18 gig. The Titan model goes from 12 meter to 25 meters at 18 gig, and it has an outboard power supply via USB at the display end. And that USB 5 volt guarantees a full 5 volts for the chipset no matter what's happening at the source or anyplace else in the system. So that's really important to make sure that that supply is consistent and there won't be any flickering or any intermittent operation with that. And we do, by the way, suggest very strongly that its AC is used in the converter that we supply. And that converter we supply that changes the AC 120 to 5 volts, that supply is a voltage regulated supply we had made specifically for us to make sure that that voltage stays within the operational range of the chip. Using the little square cubes that come with the iPhones and whatever, those are not regulated, and that voltage can swing anywhere from 2 to 7 volts and could blow the chips. So we use our device, and that makes sure that it stays. And it's included with the with all our active cables that have power supplies. Okay, the last one is Vega AOC 18 gig. This is the hybrid fiber optic cable, has the power grip connector, available from 10 meter all the way to 50, 164 feet, and fully 18 gig certified by DPL Labs. Uses the external 5 volt supply at the display end and certified 18 gig. There's with the eye pattern on that 50 meter cable. That eye pattern is a perfect eye pattern. That's what it would look like if you came directly out of the generator into the time domain analyzer. You get that same that same eye pattern. It's a perfect. So the video is absolutely perfect. And the rise time, these square waves are the rise time measurements. And remember we were saying 1.5 microseconds? Well, the Vega comes out at about a third of that. So it's well within the operating envelope for rise time. So we don't have any difficulties with the long cables and rise time. These work absolutely beautifully. So here's some, just quick, we're getting close to the end. We're still a little over, running a little bit over, but here's what's on the internet. This cable is available. You can go on and just 2.1 and you'll see it. Now this one, it really advertised some interesting stuff. It's 8K, 120, 444 HDR, 75 feet. Wow, that's pretty amazing, isn't it? For $277. Amazing. What they're not understanding, 8K at 120 hertz, HDR, which is 10-bit, 444, it's 175 gigabits. I don't think so. I don't think they know what they're doing. I don't think they understand the technology. And they're just throwing stuff out there and seeing if it sticks. So, and again, there's no police, so they can basically say anything they want. This is all over the internet. It's all kinds of claims that are going on. And of course, consumers are looking at it and buying it and saying, what the heck is this all about? I need to have this cable. So as an integrator, you got to be able to say, well, here's the real story behind this. There's some cables that are applying that they're 24G, that have 24 gig performance, and that's better than 18 gig performance. It's not so. 24 gigs just means that those 4 channels, D0, D1, D2, and clock, operating at 6 each, which all our cables do, by the way. But we don't advertise at 24 gig because it's misleading. Because if you try to operate that 24 gig at, let's say, 8K 24 frames, you can only do it at 8-bit color at 24 frames at 420. Well, at 8-bit, remember, you can't have HDR. So what's the point? I mean, you're much better off operating 4K at 24 frames, 10-bit with HDR at 422. You have a much better picture than you would 8K with standard definition. So standard dynamic range. So don't fall for that one if you see it. So we have 2.1 cables that are coming soon. They're actually ready to go, ready to be tested by HDMI as soon as they release the testing specifications. Looks like we're going to have passive cables from a 0.5 meter out to 3 meters. 3 meters looks like it's going to be the longest we can go and still be able to pass 48 gig. We're working on HDMI active cables out to 10 meter, and then active optical cables to 15 meter, and then pure fiber out to 100 meters. So that's what we're in the process of. This is a sample of one of our 3 meter cable. That's our passive 3 meter cable. And there's the 4 channels, D0, D1, and this one it is channel 1, 2, 3, and C, which was the clock channel. And you can see that that eye pattern is passed on all 4 of them. So we know that it's going to pass the video. That's not a problem. And we also know that it will pass the DDC channel square wave rise times, because that hasn't changed. That is still the same idea as we have before. So we know these will work, just a matter of getting that certification. So here's my predictions, that the CTS test will become released sometime late this year or early 2021. The first available uncompressed 48 gig will be available on terrestrial TV in early 2022. And by the way, there's a lot of TV stations that have adopted HTSC 3.0, which gives them the capability of both 4K and 8K. 4K will come first in many of the major markets. They're ready to go with this. So 4K should be coming over terrestrial TV soon, and then they don't have to change equipment to get back to get to 8K, because the ATSC 3.0 is implemented. Compressed 48G content will be available from Netflix and satellite suppliers in 2021. There is already 2.48 gig content is being transmitted via satellite from Italy to Japan on the NHK, which is the Japanese public radio station owned by the government, is transmitting 12 hours a day, 48 gig at high definition HDR at 10-bit color. 12 hours a day, they have content, and they're constantly working on that because they're ready to go into broadcast in Japan with 48 gig content. So they'll have it before we will, but it's real. It definitely is real, and it should get here. Hopefully next year we'll see some content.
Sure.
So let's see, I move my cursor, go back, and okay. So anyway, I guess that's the end. So we'll go this way. Nope. Okay, so it's not moving. Something locked up. Anyway, I think that's the end of the presentation. And thank you everyone for sitting in and staying with me. It's a long presentation, I know, but there's so much material, and it's hard to not share some of this without ruining the overall understanding of what's going on. Any questions come up, why don't you either open your mic or type it in on the thing. Oh, well, let's see, we do have some questions. Are there harmful emissions from unshielded tools? Oh, when you say harmful, Lou, not harmful to humans, but harmful to other components, and that anything that's operating up in those RF areas. And no, Mike Toomey, I no, my Zenith black and white TV with my my clinging remote control, cling, 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 cling. That one, we did get rid of that, but thanks for asking. Drew asked a question about color branding on your previous slide. Can color banding be caused by streaming services and available bandwidth from the provider? Sure. I mean, that's just a matter of bandwidth. It's a matter of data rate. If they slow the data rate down, it can happen. So that's that. Very good. Okay, and I guess I don't see any other questions. Also, if you want to open your mic, you have questions, please do that. If you want to send me an email, you have questions, joe@tributariescable.com, joe@tributariescable.com. I thank you for spending the time with us, and I hope it's added to your understanding of HDMI and make it give you a little bit more content, a little more understanding when you're out in the field talking to your customers. And anything else that you need from me, you can always call me at the company or send me an email. We could do that. And I guess that's it. So take care of yourself. And by the way, this will be up on YouTube. I'll send you a link when we have it converted over and it's ready to be linked up. But I will send you I'll send you an email with the link. Any questions?
No, but thank you, Joe, so much for your time.
Oh, you're welcome, Gloria. Thank you for taking your time. And thanks, Lou. Okay, guys, thanks again. I'm gonna be going off the air. Go grab some lunch. Hope you're doing well. Take care and be safe out there.
Thank you.